Hey everyone, and welcome. Today we are diving deep into some lecture notes on a topic that, honestly, underpins just about every piece of advanced tech we rely on, and that is surface finish. We're going to explore the hidden science behind creating that perfect surface, from the microscopic world all the way to the smart factories that are building our future. All right, so here's the game plan. We're going to start with the basics. Why do surfaces even matter so much? Then we'll take a peek into the micro world to see how we actually measure them. After that, we'll look at the tools that leave their unique signature on every part, explore the huge shift from just fixing problems to predicting them, and then wrap it all up with this amazing concept of a smart machining loop. Okay, let's jump right in. When we're talking about high-stakes industries like aerospace or medical implants, the quality of a surface is so much more than just cosmetic. We're not talking about a pretty shine. We're talking about the core performance and safety of a component. So to really wrap our heads around this, let's just start with a question. If you could zoom in, way in, like 1,000 or even 1,000,000 times, what would a perfect surface actually look like? You might be surprised to find out it's not just some perfectly flat line. And this really gets to the heart of it all: surface finish. That's the technical term for the entire microscopic landscape of a part. It's made up of these incredibly tiny peaks and valleys, which engineers call roughness and waviness. And believe it or not, this invisible texture, it can be the difference between a part that works flawlessly for decades and one that fails when you least expect it. So, if this tiny, invisible landscape is so important, how in the world do we actually see it and measure it? Well, that brings us to the really cool science of metrology, the science of measurement. Okay, so there are basically two main ways to do this. The classic way is the contact method, using a superfine stylus. Seriously, think of it like a high-tech record needle that physically traces the surface. It's perfect for checking a part after it's been made. But the real game changer? That's the non-contact methods. These use light and lasers to build a detailed map without ever touching the surface. And because they don't touch it, you can measure the part while it's being made. Now, check this out. This is a technique called focus variation microscopy. The easiest way to think about it is like a super-powered 3D camera from microscopic worlds. It builds this unbelievably detailed topographical map, and it can see subtle patterns and tiny flaws that older methods would totally miss. This is the kind of detail you need to figure out the root cause of a critical problem. So, if microscopy is like taking a super high-res photo, then laser scanning is like shooting a continuous, live video feed. By building lasers right into the manufacturing equipment, engineers can literally watch the surface finish being created in real time. This completely changes the game. Measurement isn't a final inspection anymore. It's a live data stream you can use to control the whole process. But wait, what's creating these tiny peaks and valleys in the first place? Well, a surface is always a direct reflection. It's like a signature of the tool that made it. So if you really want to understand the surface, you first have to understand the health of the cutting tool itself. And this right here, this is the absolute key to everything. The very second a cutting tool starts to wear down, even by a microscopic amount, the quality of the surface it's creating starts to get worse. The two are just directly, completely linked. There's no way around it. If you want to control the surface, you have to monitor the tool. And using that real-time laser scanning we were just talking about, researchers have actually mapped out this predictable life cycle. It's fascinating. A brand new tool starts out in a stable phase, right? It makes a really consistent, high-quality finish. Then, as it starts to wear down, the surface gets a little bit rougher, then a little rougher still. And finally, just before the tool is about to fail completely, you see these sudden, massive spikes in roughness. This predictable pattern is the key to what comes next. So this brings us to the next huge leap forward. We're moving away from a world where we make a part, check it, and then react if it's bad. Instead, we're moving into a world where we can actually predict and prevent those failures from ever even happening. What's so cool about this slide is it shows that this isn't just one breakthrough. It's a bunch of different technologies all coming together. You've got researchers using machine learning to listen to the vibrations of the machine. Others are taking these incredibly precise measurements of the tool's cutting edge. They're all basically attacking the same problem, just from different angles, all trying to predict the quality before the part is even finished. And the key here is that modern machines are being packed with all kinds of sensors. They're effectively listening to the sound of the cut, they're feeling the forces and vibrations, and they're sensing the temperature. Every single one of these data streams is like a clue, and a smart machine learning model can put all those clues together to get a live, up-to-the-second understanding of how healthy the process is. So, what's the end game? Where does all this lead? Well, when you combine this real-time sensing with that intelligent prediction, you get to the ultimate goal, a machine that can actively manage its own quality. This is what we call adaptive machining, and it is a massive shift from the old way, where you just set your parameters and kind of hope for the best. Now, the machine itself uses that live data feed to constantly tweak its own settings, adjusting its speed, its feed rate, all on the fly, to guarantee it hits a specific quality target every single time. And this slide just lays out that cycle perfectly. Step 1, monitor. Collect all that sensory data coming off the machine. Step 2, predict. An AI model analyzes that data to forecast what's about to happen. And step 3, adapt. The machine automatically changes what it's doing to compensate. This monitor, predict, adapt loop just runs over and over, creating a system that literally corrects itself. And the payoff for all this? It's huge. As the research makes clear, this data-driven approach delivers on 3 massive promises. You get higher, more consistent quality in your parts, your really expensive cutting tools last way longer, and the entire operation just becomes more efficient, which saves time and cuts down on waste. So let's just end on this thought. In a world where machines can see, predict, and adapt to guarantee their own quality, what even happens to the idea of quality control? It stops being this separate inspection step at the end of the line, and it becomes this intelligent, integrated part of the production process itself. And that right there is a truly fundamental change in how we make things,